Set, go. Welcome to the first semester review in 15 minutes. I'll be your host today. My name's Mr. Stoker. And I'll go a little faster from here on. Alright, we started the year really by talking about what is speed. And we said speed is distance divided by time. We used the Forrest Gump activity to figure that out. But we said there's a difference between speed and velocity. And one of the differences, just dropped the microphone. I'm back. One of the differences was that speed is the change in position divided by the change in time. And we also said that it had a direction to it. So velocity has, you're going north or south or to the left or to the right. Speed didn't have a direction, but velocity always does. The way we found velocity is we actually did graphs of position versus time. And when we did position versus time, it had a certain steepness to it. And that steepness, we said, is exactly what velocity is. Where you measure steepness with rise over run, which was change in position over change in time. Units for velocity. We said the units were in meters per second, or what you're more used to, miles per hour. There was a conversion between the two. So if you came up with something was, say, 14 meters per second, then the key was to times it by 2 and add a little extra. Or if you wanted to be exact, you could times it by 2.2. And so this comes out to be somewhere around 30 miles per hour, probably a little bit more. But it was just a rule of thumb to help you convert units. We said because the definition of velocity is the change in position over change in time, which we usually would write like this, we said that there's actually 3 different ways to change your position. The common one that we're used to is speeding up, but you could also change it by slowing down or changing the rate of your position or even turning, because velocity includes direction. So that was different than people's everyday model of how you can change velocity. And we had a name for change in velocity, which we called acceleration. So by definition, acceleration was how quickly you changed your velocity compared to time. And so just like there's 3 ways to change your velocity, there's 3 ways to change your acceleration, or to accelerate. Speed up, slow down, and to turn. And that's different from everyone on the street. So people on the street's idea of acceleration was it's pretty much just speeding up. We're saying no, there's a new way to think about it in physics. It's all 3. The units for that are meters per second squared, which really is meter per second every second. Or we sometimes used miles per hour per second, like when we did the car homework with the speeding up and slowing down of cars. So that was that sort of thing. Then we talked about things falling through the air. We called it free fall. And we said whenever things fall freely in the air with no air resistance, they fall at the same rate. And we couldn't actually explain why they accelerated the same in the first unit. We got to that in the second unit. But we said that they do. So something heavy, something light, they will fall with the same acceleration, which was about 10 meters per second every second. And so if you drop 2 objects, a heavy and a light one, then no air resistance, they would get to the ground at exactly the same time because they accelerated the same. We had a couple of shortcut equations besides the 2 that I've kind of listed here. And the 2 shortcut ones were velocity is acceleration times time, and distance is 1/2 acceleration times time squared. So those were the 4 equations that we had for this. The only other thing that we did in this first unit was we said we can represent motion by drawing motion maps. And remember, motion maps are a skill that helps you analyze what's going on. So we look at that and say the spacing's getting bigger, so it's accelerating, it's speeding up. If it looked like this, we'd say looks like it's pretty much going the same velocity the whole time. If it looks something like this, we could say it looks like it was slowing down. So that helped us keep track of things. So we did motion maps, we did graphs, and we did a little bit with equations. Okay, so that was the first one. What's my time? 5 minutes. Perfect. Okay. That was the first unit. The second unit that we did was force. So the force unit, we started out by defining what force is. We said force really is a push or a pull. And the units that we use to measure force, you could say either newtons, which was capital N, or we could do what we're more used to, which is pounds, lbs. Either units work for force. They're both how much you're pushing or how much you're pulling on something. We said the rule of thumb to go from one to the other is if you have pounds, let's say you have 10 pounds, then if you multiply by about 5, that's the rule of thumb for how many newtons it is. With the idea being that you wouldn't tell your mom how much she weighs in newtons. Probably a good idea not to tell your mom anything about how much she weighs in any units, but definitely not in newtons because it's always going to be 5 times bigger. Okay, so that was the start of force. So we kind of started with that, and we said whenever you make something change what it's doing, then you have to have an unbalanced force. And if you remember, we did a simulation on the computer that involved this guy pushing a filing cabinet, and the idea was how can you make the guy push the filing cabinet so it speeds up or slows down or goes at a constant velocity. You kind of had to play around with it a bit. And we realized from that that if there's an unbalanced force, that it's going to make the filing cabinet or the object change its velocity. Or we could say it'll make it accelerate. And we said if you want it to go at a constant velocity and not change, then the key was to have balanced forces. And if the forces were all balanced, then it would move at a constant velocity. Which if it's moving at constant velocity, that means a constant speed, or there was one other option. Or it could be not moving at all. That could be happening if it's a constant velocity. So we had those kind of things. Then after that, we started looking at like, remember the basketballs in space, and we said if a basketball was filled with lead and one was filled with, well, that's supposed to be the same size, pretend it is, lead and one's filled with styrofoam, in space, how could you tell them apart? And we said, well, there's something about the lead that even though they both would weigh 0 because they're floating around, that it would be tougher to move, tougher to start, tougher to stop. And we did that lab with the hacksaw blades, and putting different masses in, it would swing back and forth, and we timed it, and I gave you a mystery mass and all of that. So we ended up learning this idea of inertia, which is basically laziness. The more inertia you have, the more laziness you have, meaning you don't want to stop what you're doing, you don't want to start what you're doing. Or I said that bad. You don't want to change what you're doing, either starting or stopping. The way we measure this is with mass. And so typically it's in kilograms, although it could be grams. So that's the unit to measure inertia. If we take these ideas and we kind of take those three and put them together, we came up with Newton's second law, which is if you want to make something change what it's doing, it depends on two things. It depends on the unbalanced force, how big that is, and another name we gave unbalanced force was net force. And it also depends on the inertia, or the mass. In fact, it's the ratio between those two things. So that was Newton's second law right there. And we used that a lot. We drew pictures. In fact, we got good at pictures, right? Of if there's an object sitting right here, and the object is being pulled downward by gravity, we called that W for the weight. If it's being then pushed up by the surface, we called that the normal force. If then something was pushing on it this way and then friction was resisting, and we drew a lot of pictures to help us think about, okay, what's the total force acting on something? And that total force, or the leftover force, whatever is unbalanced, became our net force. So the pictures, the force diagrams, were just to help you figure out what the unbalanced or the net force was. So you had quite a few problems with this, like numbers that you had to work out. For example, if the push was, let's say, 50 newtons, and let's say friction was 15 newtons, and the weight was 20 newtons, and then normal force, I could say, oh, that's got to be the same size as the weight because those balance out. Also 20 newtons. So what's unbalanced here, or the net force in this case, is just the 50 minus the 15, which is 35 newtons. So then I could figure out what the acceleration is. 35 newtons unbalanced. I could say if the weight is 20 newtons, then that means the mass of this thing must have been 2 kilograms. Because remember, the strength of gravity pulls with, the strength of the gravitational field is 10 newtons per kilogram. So if something was 2 kilograms times it by 10, you get the weight 20 newtons. So then I would divide by that inertia, 2 kilograms. I usually would be given this and not have to figure it out, which means this is like 17.5 meters per second squared for the acceleration. We did a little bit with Newton's third law as well. So to kind of sum this up, this was Newton's first law here. This was Newton's second law there. And Newton's third law was forces always occur in pairs. And another way to say that, for every action, there's an equal and opposite reaction. So if I am throwing an object here with really long arms, I'm like an ape or something, and I'm throwing this object, I'd say, okay, I'm pushing on the object with a force, but then the object is pushing back on me with an equal force. Now those forces don't cancel out because they're acting on different things, but they are equal in size. But don't expect forces that are the same size to produce the same acceleration, because the ball or the object I'm throwing probably has a very small mass, which gives a big acceleration. Meanwhile, the person has a much larger mass, so that gives a much smaller acceleration. So we did a lot of stuff with Newton's third law. The last thing that we did is we said, why is it that objects fall at the same acceleration? Take something light and something heavy. Gravity's going to pull on the light thing with a small force. Gravity's going to pull on the heavy thing with a big force. So why would they accelerate the same? Well, because this has a lot of inertia and that has a small inertia. So the ratio of force to mass was about 10 for this guy when it's falling. The ratio for force to mass here is also about 10. So now we can explain why things accelerate the same. What's my time now? Holy Moses. Okay. Let me talk about air resistance real quick. Air resistance, when things fall with air resistance, they don't fall the same rate, because now we have something pushing back up on them, and a small air resistance pushing back up can cancel out that guy, but a big one, big force of gravity here, is not canceled out by the air resistance here. So a heavier thing will fall faster and get to the ground quicker. Okay, let me talk about energy real quick. We've just gone over energy. This should be most fresh in your mind. We said energy is the ability to cause change or pain. We said we measure this in units of joules. That's like calories. 4,000 joules is 1 calorie. That was the rule of thumb for that one. We had potential energy due to gravity, mass times gravity times height. We had kinetic, 1/2 mass times velocity squared. We said work is whenever there's a transfer of energy by a force. It's also equal to force times distance. And we said power is what you get when you transfer energy or do work and divide it by time. These units for power were in watts, which is capital W, and to solve energy problems we used pie charts. Maybe this becomes part kinetic, and then maybe at the end it becomes all kinetic. We also had dissipated energy and potential energy elastic, stored in something springy. We didn't have formulas for those, but we did write things down for them. The end. What's my time? 15:25. I'll take that.